Hi, we are Team 65 and we're here to present our Design Challenge 1, the Impossible Puzzle. Our clients pitched us the Impossible Puzzle, a puzzle that places a puzzle piece that is pushed out that makes it impossible to solve. This was meant to help learn anger management and Purdue grit. The specs given to us by clients were two parts that fit together, and when they're fit together, a robot pushes them apart. We created technical requirements based on the client needs that were given to us. The first client need being ease of use, and we gave that the technical requirement of puzzle piece radius. And a radius of maximum 3 millimeters was given to the puzzle piece. This makes it so that the user, no matter who they are, can easily push in a piece to the puzzle. And next was inducing anger as a client need so that they can develop the skills of the user for anger management. And we gave that the autonomous pushing mechanism success rate of at least 95%, so that the puzzle piece is pushed out whenever placed by the user so that they are consistently angered by not being able to use the puzzle. We then created target values. We set a radius of maximum to be 2.5 milliliters, just to guarantee that it was easy to use. We want that to be our target. And secondly, a 100% success rate. We feel that the best success rate would be 100% because the user never gets the joy of pushing that piece in, and they're always faced with the anger of keep pushing it out, pushing it out, pushing out. And so they learn the skills for anger management and Purdue grit to keep going, keep going, keep going.
Okay, so these are the main design considerations we had when we were designing our solution to the problem. So the first thing we needed to understand was how we were going to detect when the puzzle piece was put in to the grid that we had designed. So we had two options for this. We had a touch sensor and an ultrasonic sensor, but we realized that the ultrasonic sensor wouldn't be able to have that sort of precision to detect when a single pin went in. So that's why we opted to use the touch sensor and made it part of the pusher arm that ended up being used in the final design. Another design consideration we had was the orientation of the system. We had to realize that, or we had to plan to either have the puzzle laid out in a horizontal or a vertical orientation. And what we noticed is that when the puzzle was laid out in the vertical position, we did not have the pieces in our kit to actually stabilize it vertically. So we laid down the puzzle horizontally and just let it lay flat so that you could see the inner workings of the system, but you wouldn't have to build any sort of support system using parts that were included in the kits that were at our table. We also wanted to make sure that the physical puzzle piece that we used was appropriate for our puzzle, and we tried pegs and axles. And we realized that the best piece to use was a peg that had the cross section on it and one that wouldn't fully have a lot of friction inside the peg hole. That way, when the pusher arm pushed the peg would come out easily, and we wouldn't need to worry about there not being enough torque or enough force to push those pegs out. So we were inspired by a few different things in the real world, a couple of already built contraptions. The primary one was the wheels of a train, and how as the wheels spun, it was still able to create a linear action through the use of these arms. And we sort of modeled this in our final design through the use of connecting a gear to this final arm piece. And what that does is as the motor turns the gear, the linear actuator still can go in and out, and that's what helps create that pushing action that gets the peg out of the hole.
Now that you've seen an overview of our project's design considerations and the various decisions we made along the way to finalize our design, along with the automated pushing system, here's a small video of the functioning of our project. As you can see, as the user inputs the puzzle piece into the robot automatically pushes the puzzle piece outside, sensing that the touch sensor has been activated. You can also see the automated pushing system aiding in this automated pushing mechanism. This is a snapshot of the code of the Raspberry Pi used in this robot. And we use two major modules. One is the BrickPy 3 for Raspberry Pis, and the other one is a time module, which is default a Python module for pausing the code when used in like time.sleep, as you can see in the try statement. In our code, we have an offset motor encoder function, which sets the motor value to 0, irrespective of where it starts. So when we use the touch sensor, the motor value just revolves 360 degrees. And again, it sets the motor value to 0 when it comes back to using the touch sensor. So this is a small snapshot of it. And there's only one while loop inside the try. And there's an except for just a sensor error and the keyboard interrupt. So in conclusion, this is the impossible puzzle. Our robot that autonomously pushes and prevents a user from placing a puzzle piece into the actual design. And this results in extreme anger from the user and leads them to find ways to cope with that anger. All this hard work will introduce them to Purdue Grit. Thank you.